Alrighty, well, we are at the 8:05 mark. I think we're ready to go ahead and begin. Just so y'all are aware, we're going to be operating the question and answer Q&A. It's usually at the bottom of the Zoom window. If you have any questions that you'd like to make, you can make them throughout the presentation, but we're going to be fielding them at the end. Wayne is going to be presenting this evening, and he's got his notes and everything ready to go. So without further ado, Wayne, if you would like to begin, you have the floor.
Thank you. So good evening, everybody that's attending. Welcome to our second webinar on anthropogenic or man-made global warming. Tonight, we are going to examine the impacts of increased global temperature on land from the perspective of land use. We'll be concerned with degradation and loss of land as a source of life for humanity and for nature. As we will see, human decisions about land use cannot be ignored when assessing the impacts of continued warming. And humanity and the climate conditions we find ourselves under are tied together in a complex relationship of cause and effect. Whether land becomes degraded or remains a stable source of life depends on both physical conditions and human conditions. Next slide, please. In creating this presentation, we've relied on several sources of information. The IPCC 6th Assessment Reports, published between 2019 and 2022, have provided material on how impacts on land are determined, what the impacts are, and what the future might hold. The World Atlas of Desertification, in particular, Chapter 5, Convergence of Evidence, has provided additional details and impact assessments, as well as some graphical ways of looking at factors that are present in the global land surface area. Next slide, please. So what is the current state of global land use? How do we distribute land today between agriculture, forest, and rangeland? Next slide. About 3/4 of the global ice-free land surface by the year 2015 was affected by human use. Today, humans appropriate 1/4 to 1/3 or more of global terrestrial potential net primary production. Next slide. One way that humans appropriate the productive potential of land is through agriculture. Croplands cover 12 to 14% of the global ice-free surface area. In this U.S. Geological Survey image, which is derived from satellite data at 30 meters of resolution, the green areas represent the distribution of most croplands on the globe. These areas are the bulk of the sources of food, feed, fiber that support our near 8 billion population. This does not mean that the darker areas have no agricultural production, but that the concentration of production as a percent of land area is low. Next slide. This NASA image indicates forested areas of the globe using the definition of forested area as a 30% tree coverage per pixel. Human activities cover at least 60% of this area. Next slide. Human use affects 70 to 90% of other natural ecosystems. This map, produced by UN and nonprofit contributors to the Rangelands Atlas, describes the type and area covered by various classifications of rangeland across the world. We are accustomed to associating rangeland with cattle grazing, and it often is. But there are different types of rangeland cover, and rangelands can be homes to wildlife and natural ecosystems. Savannas and natural grasslands are indicated on this map. Natural grasslands are indicated on this map by the light green and brown areas, but human influence reaches into other types of rangeland as well. Next slide. This chart shows the percent exploitation of land types. Cropland accounts for 12 to 14% described earlier, but it is the most intensively exploited. I should have said the chart shows the distribution of land types. The intensity of exploitation I'll describe in the text. So croplands only cover 12 to 14%, but they're the most intensely exploited. Rangelands are the next most exploited, with 16% of savannas and shrublands. Forests make another 22% of the total exploited ice-free surface area. Only 16% of the ice-free Earth remains relatively free of exploitation. The remaining 12% of the surface is barren rock. Although not shown, 17% of the Earth is supposed to be protected area. There is widespread agreement that protected areas are under pressure from human activities, and that at least 30% of the Earth's land should be protected to mitigate climate change and preserve some biodiversity. Next slide. So as the IPCC report notes, humanity is completely, utterly dependent on the productive capacity of land to survive. We have introduced into the natural productive potential of the Earth, with no signs of slowing down, increasing land-air surface temperatures. We know that global warming due to the production of greenhouse gases that trap and irradiate heat is occurring. Globally averaged land surface air temperature has risen faster than the global mean surface temperature from the period 1850-1900 to the present day. Mean land surface air temperature has increased by 1.53 degrees centigrade, while global mean surface temperature has increased by 0.87 degrees centigrade. Next slide. The IPCC report data stops at 2018, but for global mean surface temperature, other sources are available. One of those sources is the National Oceanic and Atmospheric Administration, sometimes referred to as NOAA, which uses a baseline of average 20th century mean land ocean temperature. The NOAA baseline average value for the 20th century was 12C, which, as the previous figure showed, was already above the IPCC baseline for the 1850 to 1900 period. So to compare the previous figure, if you added around 0.25 degrees C to the numbers, it would match the previous figure. What this shows us is that all of the 10 hottest years on record have occurred in the 21st century. In fact, since 2010, 2016 is currently the hottest year on record. Next slide. NASA has developed a useful interactive map that will show global distribution of temperatures from 1884 to 2022, with the average temperature measured from 1951 to 1980 shown as 0 on the scale on the bottom of the screen. Note that the scale here is in degrees Fahrenheit. The low end of the scale would be minus 2.22 degrees C. The high end of the scale would be plus 2.22 degrees C. So this is a representation of the data set for 1884. This is what the world would have looked like in terms of heat distribution in 1884. Next slide. This shows us the data representation for the year 1980. It shows the world is starting to warm up across the globe. And finally, what we see, next slide, is the relative change in temperature as shown in the year 2022, where with the exception of some ocean areas, the planet is mostly warmer. Europe, parts of Russia, the Arctic, and parts of China already having experienced the 2 degrees C rise for 2022 that we hope will not be the long-term average increase. Note that 2022 is still not the warmest year on record. Next slide. So we're not showing any signs of slowing down. This NOAA chart, which was published in an April 2023 article in Guardian, showed the average temperature at the ocean surface has been at about 21.1 C since the start of April, beating the previous high of 21 C set in 2016. This is important for land because ocean surface temperatures are a big contributor to heat waves over land. 2023 might very well be hotter than 2016. Next slide. We know that changes in land and ocean temperatures have initiated processes that have had negative impacts on land productivity. But land, no matter what its use, also interacts with climate. Because humans practice land management or mismanagement, as the case may be, human decisions and actions become driving forces in land productivity through physical changes in land. The altered land then interacts with the climate in its own ways. These interactions create various cycles of energy exchange, greenhouse gas production, carbon exchange, production of nitrogen and nitrogen exchange, and exchanges of water through evaporation and evapotranspiration. Land surface characteristics such as albedo and emissivity determine the amount of solar and long wave radiation that is absorbed by land and reflected or emitted to the atmosphere. Surface roughness influences turbulent exchanges of momentum, energy, water, and bio and geochemical tracers. Land ecosystems modulate the atmospheric composition through exchanges of many greenhouse gases and through precursors of what are called short-lived climate forcers. These include biogenic volatile organic compounds, and they also include mineral dust. Atmospheric aerosols that are formed by these precursors affect regional climate by altering the amounts of precipitation and radiation reaching land surfaces through their role in the physics of clouds. The result is a complex web of interactions whose predicted outcome depends on our ability to identify these exchanges and quantify the magnitudes that are associated with them. Next slide, please. So when people talk about potential losses from the alteration of the Earth's climate, they mean a loss of productivity. Sometimes this productivity is crop yields or numbers of livestock that can graze in a particular range. Freshwater lakes, rivers, and groundwater stocks can become overused or simply dry up. Sometimes it is loss of biodiversity or what are called ecosystem services. For these losses to come about, land has to change in negative ways or degrade. Next slide, please. Excuse me. So what are ecosystem services? Ecosystem services were defined in the 2005 UN Millennium Ecosystems Assessment, specifically the report Ecosystems and Human Wellbeing, a framework for assessment. And ecosystem service is any of the direct and indirect contributions of ecosystems to human well-being and have an impact on our survival and quality of life. Ecosystem services are classified as provisioning services, regulating services, cultural, and supporting services, which may have some overlap. Next slide, please. Provisioning ecosystem services include food, potable water, fuel, fiber, a source of naturally occurring chemicals that are useful for humans and animals, such as medicinal plants, and a pool of genetic resources for biotechnology and species evolution. Regulating services are feedbacks to that influence climate, have adapted to limit disease through natural means. If we disturb an ecosystem, we run the risk of creating new niches for pathogens and creating new means of transmission. Regulating services filter water for use by animals and humans. And there are also services such as pollination, which are crucial for plant survival and human agriculture. Cultural services are based on the interaction of humans with the environment as societies develop and learn. Cultural practices developed by humanity over the centuries were often interwoven with the environment. And the environment is also a source of aesthetic pleasure. Finally, we have supporting services. We have soil formation, nutrient cycling, and primary production, which is the generation of biochemical compounds and precursors for use by elements of the ecosystem. Supporting services generally take place over long time scales. A couple of points worth noting. One is that ecosystem services and biodiversity are related, and a system with poor biodiversity is not likely to provide strong services. Natural ecosystems rely on many species operating together to provide services. The other is that an ecosystem here does not necessarily mean a 100% natural, untouched by man collaboration of species and environment. An ecosystem can be described within the confines of agricultural practice or managed woodlands and still provide some of these services. This has led some people to try to quantify ecosystem services in economic terms. Next slide, please. So we're concerned with the loss of productivity, ecosystem services, and biodiversity through the degradation of land. The IPCC special report on climate change and land draws a distinction between land degradation and desertification. This is not a question of processes. Desertification is land degradation, but desertification refers to land degradation in environments that are defined as arid, semi-arid, or dry subhumid. Outside of the scientific community, this might seem like a distinction without a difference, with desertification being an extreme case of degradation. However, land may become less productive. Ecologies may be altered in varying degrees depending on changes in land short of the extreme of desertification. Also, there has been much debate on land degradation and its extent among scientists from different disciplines. Currently, these debates are being resolved under the umbrella of a new interdisciplinary science, referred to appropriately enough as land change science. For purposes of this presentation, we're going to adopt the IPCC definition of land as shown in bullet 1. Land degradation as a blanket term applicable to all land areas, regardless of geography, in bullet 2, and desertification is a special case of land degradation in bullet 3. Land is the terrestrial portion of the biosphere that comprises the natural resources, the ecological processes, topography, human settlements, and infrastructure that operate within that system. This framing places humans and their activities within land as a functional element in the processes and land undergoes on a daily basis. Land degradation is a negative trend in land condition caused by direct or indirect human-induced processes, including climate change, expressed as long-term reduction or the loss of biological productivity, ecological integrity, or other value to humans. Land degradation has accompanied humans at least since the introduction of agriculture, but today this is accelerated by global warming. Desertification is land degradation in arid, semi-arid, and dry subhumid areas, resulting from many factors, including climatic variations and human activities. Next slide, please. Deserts are specific ecological and productive systems, and desertification may apply to lands on their fringes, but not to the desert itself. Aridity is a condition characterized by low average precipitation or low availability of water. Drought is a climatic event that can occur anywhere. Dry lands are regions of the earth which have aridity indices of 0.65 or below. That means the ratio of available precipitation to the potential for evaporation and evapotranspiration, which is a measure of ground vegetation, is 0.65 or less. Next slide, please. The IPCC distinguishes between land degradation and desertification, and it treats assessments, observations, and predictions of both in separate sections of the 6th assessment reports. Because of time constraints, we're going to focus tonight on desertification. The IPCC identifies processes of desertification and drivers of desertification. Processes are the biological and physical events that contribute to a reduction in productivity of land, with desertification being the extreme outcome. Such processes are global warming and reduced rainfall, which lead to a loss of water from plants as evapotranspiration increases in the intensity and duration of wildfires, which damage land directly by destroying land cover, fertility, and soil microorganisms. And we have the problem where invasive plant species may replace previously existing vegetation. For example, woody plants may replace grasses. Since woody plants are more sparsely distributed than grasses, land between the plants becomes subject to erosion from heavy precipitation. Next slide, please. An example of invasive plants contributing to degradation is the Great Basin region in the western United States. Over 20% of Great Basin ecosystems have been significantly altered by invasive plants, in this case, exotic annual grasses and invasive conifers. This land cover conversion has resulted in reductions in forage availability, wildlife habitat, and biodiversity. Next slide, please. Drivers of desertification are the human decisions and actions that can contribute to desertification. A few of the drivers are expansion of croplands. Croplands can expand, displacing existing ecosystems such as forest or grasslands with agricultural uses. Crops may be farmed in a way that destroys topsoil, making it vulnerable to erosion. Over-extraction of groundwater to irrigate crops can deplete groundwater, which remains low because precipitation is reduced. Climate or hydrological changes can cause soil salinization, increases the mineralized groundwater level or the mineralization content in groundwater. Secondary salinization occurs when the concentration of dissolved salts in water and soil is increased by anthropogenic processes, mainly through poorly managed irrigation schemes. Deforestation accompanies any number of human activities, including expansion of agriculture, including livestock, extractive industry, and urban expansion. Human appropriation of land for building denudes land, reducing ground cover and increasing local temperatures. Extractive industries have similar effects, interrupting ecosystem services across wide areas through topsoil, or as we have seen in the US, entire mountains. Next slide, please. Excuse me. The World Atlas of Desertification that was first published in 1992 has a similar approach to assessment of desertification. This approach is rooted in the difficulties of mapping desertification without the integration of many types of data, and also the input of ground observers and regional experts. Therefore, rather than produce uncertain and possibly misleading maps, the Atlas seeks to make available to experts and observers such data as can be provided that shows evidence for one or more of these global change issues, as they're called. The local, regional, or national people trying to assess the condition of an area in terms of progress toward or away from desertification can see the impact on the region of issues where they lack data, or they can note that there's a multiplicity of issues that they may not have been able to observe directly. On-the-ground observers can then augment this data with their own measurements and make better assessments for remedial action or recommendations. The Atlas provides to users two different types of data, within which there are subtypes. The first data type is land cover and land use, which broadly classifies land as cropland, rangeland, or forest. These may be dry land or non-dry land. Cropland may be more modified further by a range of conditions such as rain-fed versus irrigated, or having excess nitrogen versus being nitrogen deficient. The second data type represents global change issues. These issues can be categorized as biophysical or socioeconomic. Both types of issues increase the risk of desertification, and the presence of multiple issues is a stronger indication of risk. This slide lists part of the different biophysical change issues used in the Atlas's determinations of states of desertification. Aridity index less than 0.65. Water stress. This is where human withdrawal of groundwater exceeds 40% of the sum of the surface water and the groundwater that's available in a year. Decreasing land productivity. It's rated either severe or moderate, depending on the accumulation of biomass in a growing season. This is a proxy measurement for net primary productivity, which we'll talk about shortly, which measures the net carbon exchange between plants and atmosphere from photosynthesis and respiration. Next slide. Remaining biophysical change issues, climate vegetation trends. It reflects the below average productivity and biomass due to drought. Fires, how often and how many fires occur over some period. And tree loss, the yearly decline in tree cover. Next slide. More socioeconomic indicators, population density. the population density being greater than some broad land cover class median, usually within a country. Population density, the number of people per square kilometer, is derived from census data. Population change, it's a change in the population density. It reflects an increase in the number of people in a certain area. And the income level, which is just the average income of a country's citizens computed on the gross national income divided by the size of the population. Next slide. Built up area change is a socioeconomic indicator. It increases, it expresses the percent of square kilometers that are observed to be covered by building construction when it is greater than a certain median value for that land type. This is derived from high resolution satellite observations and can be augmented by other information. We have the problem of low input agriculture, where a nitrogen deficit exists. The nitrogen balance indicates the level at which crops use the applied nitrogen according to local conditions is in deficit. And we also have high input agriculture where a nitrogen surplus exists. Next slide. Finally, we have irrigation. Irrigation occurs in greater than 10% of a 100 square kilometer area, obtained by combining subnational irrigation statistics with satellite information. And finally, we have livestock density. Livestock density is greater than some median for that particular type of livestock. They're calculated in terms of units. A cow is 0.8 LSUs. A chicken is only 0.01 LSUs. The density of livestock is related to environmental pressures produced by land use change, which could mean deforestation. Overgrazing becomes a risk, as well as increased greenhouse gas emissions. They didn't identify what a 1.0 LSU is. I suppose that's an elephant or a camel. Next slide. So the World Atlas of Desertification shows the 6 most common arrangements of change issues that appear in areas at risk of desertification. It's remarkable in this set of arrangements for the 6 most common GCIs, India appears in 4 of them. Common to all scenarios in India are aridity, water stress, population density, population change, income level, high input agriculture, irrigation, and livestock density. Across all the regions that are at risk, aridity, population density, increasing population, and livestock density are common factors. We also see that high input agriculture is common to 5 of the 6 most common GCIs, as is income level and the use of irrigation. Next slide, please. We've said that it's difficult to produce maps that show the extent of desertification or degradation, but it is possible to point out the presence of processes and drivers or global change issues. Excuse me. One such GCI is aridity. Aridity alone will not determine that desertification is happening, but it does create risk. This image maps the global extent of lands that are classified as dry lands and shows where aridity combined with other pressures such as increasing temperature or high population density might lead to desertification. While aridity accompanied by drought and other issues has certainly caused desertification and increases risk, scientists have recognized that in an environment where CO2 is constantly increasing, these factors do not necessarily mean imminent desertification. Increasing atmospheric CO2 has effects on plant growth that may result in increases in productivity by stimulating vegetation growth. However, as the land surface air temperature continues to increase and lack of precipitation and increased evapotranspiration occur, the effect of the increased CO uptake can be reversed. Next slide, please. So none of the limitations or reservations that have been expressed about evaluation or of desertification or land degradation mean that we cannot use the broad data gathered to date to make some conclusions about global, regional, or even country level land conditions, whether they are stable, stressed, or actively degrading. Next slide. The IPCC observations about stages of land desertification and degradation, as well as other assertions, are made with levels of confidence: very high, high, medium, and low. Confidence is the robustness of a finding based on the type, amount, quality, and consistency of evidence, and on the degree of agreement across multiple lines of evidence. Next slide. Net primary production, which we mentioned earlier, another term frequently used in IPCC reports. This is the amount of carbon accumulated through photosynthesis minus the amount lost by plant respiration over a specified time period that would prevail in the absence of land use. In other words, in the absence of human use of a particular area, this would be the potential carbon exchange between vegetation and the environment within the natural ecosystem of that area. Next slide, please. So some general IPCC observations on land. Land, including its water bodies, provides the basis for human livelihoods and well-being through primary productivity, the supply of food, fresh water, and multiple other ecosystem services. This statement seems obvious enough, but humans often view their interactions with land through the lens of immediacy, which means they are concerned with conditions confronting them at the moment. If before every decision that was made about land use, reflection upon this statement was required, perhaps there would be fewer bad decisions. Another equally important statement is that the Earth's land area is finite. The IPCC has very high confidence that using land resources sustainably is fundamental for human well-being. Next slide. The IPCC also notes that the current geographic spread of the use of land, the large appropriation of multiple ecosystem services, and the loss of biodiversity are unprecedented in human history. In other words, we've never been here before. We cannot point to some comparable global set of conditions in our past for elimination, and that alone should give us pause on considering the possible future we are creating. An accompanying IPCC medium confidence observation is that our unprecedented land use caused global biodiversity to decrease by 11 to 14%. The IPCC notes that between 2007 and 2016, agriculture, forestry, and other land use contributed about 23% of anthropogenic emissions of greenhouse gases. The IPCC reports this as a medium confidence observation, but it follows that observation with a high confidence observation that says agriculture, forestry, and other land use results in both emissions and removals of carbon dioxide, methane, and nitrous oxide to and from the atmosphere. The medium confidence designation in the first statement comes from the recognition that the interaction between land and climate makes separating the anthropogenic component of emissions somewhat difficult. Excuse me. So news and public discourse often focuses on the emissions caused by power plants and concentrated industrial activity. But this observation makes it clear that the aggregated actions of humans in geographically dispersed places can have significant impacts. Next slide. The IPCC makes many recommendations in the special report on climate change and land that cover desertification, land degradation, and food security. We'll consider food security in a future webinar. For the present, let's just look at the processes and drivers of desertification. One observation is that we are seeing since 1961 a 1% per year increase in areas already classified as dry land that are subject to drought. Drought is one of those processes that can drive desertification. At the same time, as the percentage of dry lands experiencing drought increases, as the percentage of dry lands experiencing increasing instances of drought rises, the population in those areas is rising also. In 2015, at least 380 million people and possibly as many as 600 million live within areas which experienced desertification between the 1980s and 2000s. The IPCC lists that as a low confidence observation, which is associated with the difficulties of getting accurate population numbers in these areas. We see also a decline in inland wetland extent, meaning the areas previously described as wetlands are shifting to higher aridity, if not yet defined as drylands. Next slide, please. The highest numbers of people affected are in the South and East Asia, the Circum-Sahara region, including North Africa, and the Middle East, including the Arabian Peninsula. This is a low confidence observation that again reflects the difficulties of estimating populations and shifts in populations in these areas. Other dryland regions have also experienced desertification. People living in already degraded or desertified areas are increasingly negatively affected by climate change. This is a high confidence observation. There's a lot of agreement across multiple lines of evidence. In some dryland areas, increased land surface air temperature and evapotranspiration and decreased precipitation amount in interaction with climate variability and human activities have contributed to desertification. These areas include sub-Saharan Africa, parts of East and Central Asia, and Australia. They have medium confidence in this. There is medium agreement across multiple lines of evidence that in some areas, the processes of increased land surface air temperature, evapotranspiration, decreased precipitation, and drivers of human activity have increased the instances of desertification. Next slide, please. Certification amplifies global warming through the release of carbon dioxide linked with the decrease in vegetation cover. That's a high confidence observation. Desertification processes such as soil erosion, secondary salinization, and overgrazing have negatively impacted provisioning ecosystem services in dry lands, particularly food and fodder production. Another high confidence observation. Loss of provisioning ecosystem services to humans and to wildlife feeds into loss of biodiversity in dry lands, where biodiversity is meant to include plant as well as animal species. Drylands are home to over 20% of global plant centers of biodiversity, defined as areas where groups of plants, animals, and other organisms had their genetic origins. Plant species located within these areas are often highly threatened by climate change and desertification. For example, in the southwestern Algerian steppes, plant species richness decreased from 234 species in 1978 to only 95 in 2011, following long periods of drought and human-driven degradation. Other dryland areas are home to 30% of endemic bird species and 25% of vertebrate species. Finally, the IPCC observes that desertification, including through land use change, already contribute to the loss of biodiversity across drylands with medium confidence. The medium confidence designation indicates that the scientific contributors to the report are aware of loss of diversity across drylands, but have not resolved all the issues associated with measuring the scale of the loss. In the Climate Change 2022 AR6 report, Impacts, Adaptation, and Vulnerability, in the technical summary, the assertion is also made with very high confidence that climate change has caused local species loss, increases in disease, and mass mortality events of plants and animals. Next slide. The IPCC does have some regional observations about desertification across the globe by region. So let's look at a few of those. It's estimated that 46 of the 54 countries in Africa are vulnerable to desertification, with some already affected. Moderate or higher severity degradation over recent decades has been identified in many river basins. The Nile Basin, 42% of its area. The Niger Basin, 50% of its area. Senegal, 51%. Volta, 67%. Limpopo, 66%. Lake Chad, 26%. Between 1986 and 2015, 18.6% of forest cover around the Owena River Basin in Benin was lost. Next slide. Between 1982 and 2003, when accounting for CO2 and various nitrogen compounds fertilization, 65% of the land mass of the Volta River Basin, that's parts of Mali, Cote d'Ivoire, Benin, Togo, Burkina Faso, and Ghana, have been degraded. The Horn of Africa, Ethiopia, Somalia, Eritrea, Djibouti is getting drier, exacerbating the desertification that is already occurring. Based on NDVI residuals, Kenya experienced persistent negative vegetation trends over 21.6% of the country for the period 1992 to 2015. Kenya is currently facing its 6th consecutive year of insufficient rainfall. The NDVI residual stands for Normalized Difference Vegetation Index. It's a measure used in satellite monitoring of vegetative land cover, relying on near infrared and infrared radiation measurements over time as a proxy for net primary production. Next slide, please. Kenya has experienced 3 separate drought events spanning the last 6 years. These droughts have caused massive die-offs of wildlife and cattle. Between February and March of 2022, Kenya documented the deaths of 205 elephants, 512 wildebeest, 381 common zebras, 51 buffaloes, 49 of Grevy's zebra, and 12 giraffes. As of March 2023, the drought situation in 21 of the 23 Kenyan counties is critical. Acute malnutrition has been noticed across the counties, with over 970,000 children aged 6 to 59 months and over 142,000 pregnant and breastfeeding mothers currently malnourished and acutely in need of treatment. The number of people in Kenya facing severe hunger is expected to rise to 5.4 million this year, particularly in the north of the country, where about 95% of the surface water sources have dried up. Next slide, please. In Europe, much of the threat of desertification occurs in the Mediterranean countries. Dry lands cover 33.8% of northern Mediterranean countries, approximately 69% of Spain, 66% of Cyprus, and between 16% and 62% in Greece, Portugal, Italy, and France. The European Environment Agency indicated that 14 million hectares, which is about 34.6 million acres, 8% of the total EU territory, mostly in Bulgaria, Cyprus, Greece, Italy, Romania, Spain, and Portugal, had high or very high sensitivity to desertification. If we include moderately sensitive areas, that figure increases to 40 megahectares, which is 23% of the European Union territory. Desertification in this region is driven by irrigation developments and encroachment of cultivation on rangelands caused by population growth, agricultural policies, and markets. Next slide, please. For Spain alone, it was estimated that soil erosion can be 300 metric tons per hectare a year, which is equivalent to losing 18 millimeters or 0.7 inches of surface soil every year. Earlier, we talked about the ecosystem service of primary production. Topsoil production is primary production. And if 18 millimeters doesn't sound like a lot, consider that under natural conditions, it will take more than 100 years to replace 1 inch or 25.4 millimeters of topsoil. That in most places, there isn't all that much topsoil to begin with. So to lose 18 millimeters every year is a terrible blow. About 7% or 130 million hectares of land in Russia was threatened by desertification by 2000. In Turkey, hydrological and climate conditions threaten about 60% of Turkey's land area. 48% of Turkey's land area is prone to moderate to high desertification. Next slide, please. So as we see, we have desertification occurring in areas of dense population. This is also true across Asia, with China and India experiencing significant confluences of biophysical and socioeconomic issues. What does the World Atlas of Desertification have to say about risk of desertification in specific areas? We've talked about the land use definitions used by the World Atlas of Desertification and their modifiers, which create combinations of use with respect to cropland. The Atlas makes global observations about these combinations, as well as some specific regional observations. The possible combinations of Atlas land use combined with the regional observations are too extensive for us to cover here. So we will look at global observations for one, with a few examples of regional observations. Next slide, please. So the observations made by the Atlas scientific team are based on a principle called convergence of evidence. It states that no global change issue by itself is sufficient to infer a change in land status from stable to degraded or degraded to desertifying. However, where multiple GCIs converge, it indicates to researchers that the area is under threat of degradation and these areas need attention. Since multiple GCIs occur in many areas, there is much happening across the globe that should be cause for alarm by governments, institutions, and people. Next slide, please. Let's look at the World Atlas global observations of GCIs with respect to the land classification high-density croplands, which means that more than 50% of every square kilometer is cultivated. More than 50% of high-density croplands are affected by high population density, high livestock density, and high fertilizer input, which means that the high nitrogen balance or excess nitrogen. Excess nitrogen is associated with the formation of atmospheric nitrogen-oxygen compounds and nitrogen runoff into water sources. This graph quantifies the percentages of high-density cropland affected by the GCIs on the left axis. For example, it shows that high livestock density affects more than 60% of dry land areas and close to 30% of non-dry land areas. We see that high population density affects around 20% of high-density non-dry land croplands and around 40% of high-density dry land croplands. This means those areas will place demands on food production and water use. If population change is present, meaning population increase, there will be pressure to change land use patterns from cropland, rangeland, or forest to built-up areas, as well as increased water stress. Of course, as we have seen, changes in land mean changes in land climate interaction, with declining land and losing carbon to the atmosphere, increasing erosion potential and contributing to atmospheric dust and to sand. Next slide, please. Approximately 9% of high-density cropland area experiences potential pressure from 8 to 13 GCIs, most of it in dry lands. Signs of land productivity decline are observed in 23% of this area. Approximately 60% of high-density cropland has from 4 to 7 GCIs, which is split roughly evenly between dry land and non-dry land areas. Only 20% of this area, they coincide with trends in declining land productivity. Next slide, please. Approximately 29% of high-density cropland experiences potential pressure from 1 to 3 GCIs. Approximately 11.5%, or 500,000 square kilometers, show signs of declining land productivity. Only 2% of high-density cropland across the globe, all non-dry lands, are not associated with any pressures from any of the global change issues. Next slide, please. So the Atlas makes some regional observations about the impact of GCIs on high-density croplands. Global regions where high-density cropland coincide with global change issues are sub-Saharan Africa, including Burkina Faso, northern Nigeria, eastern Sudan, South Kenya, Malawi, and Zimbabwe. In North Africa, northern Morocco, the Egyptian Nile area, and the Tigris-Euphrates region is affected. In Asia, India, Pakistan, and across cropland agricultural, in Asia, India, cropland in Pakistan, and agricultural expansion areas in Northwest China are affected by GCIs. In Central Asia, the Aral Sea area, Eastern Kazakhstan, Uzbekistan, Kyrgyzstan, and Tajikistan are affected by GCIs. Next slide, please. Other global regions that are where this is an issue in Latin America and the Caribbean, the Northeast Brazilian drylands, agricultural expansion areas in the Argentinian Chaco, central Chile, cropland in southern Mexico, and parts of Cuba and Haiti. In Australia, southeast and southwest areas are affected. In the United States, irrigated in the areas in the west are affected by global change issues. Next slide. Africa has more GCIs present in high-density cropland than most other continents. Over 80% of their high-density cropland has high population densities and population increase. More than 75% of that land is arid. It has low per capita income, and almost 75% has high livestock density. In Asia, more than 58% of high-density cropland has 6 or more GCIs. 75% have high population densities, livestock densities, and fertilizer use. More than 50% is arid with high water stress, irrigation, high population growth, and low incomes. In Europe, we have GCIs that cover more than 25% of the area, including population density, livestock density, and high input agriculture. In addition to these, in Southern Europe, the area around the Mediterranean and the areas that we talked about earlier also undergo water stress. Confirming the IPCC observations, larger numbers of coinciding GCIs are generally found in the southern part of the continent. Change in built-up area is the largest of any continent, and it occurs on 16.3% of the area. Next slide, please. So in North America, about 30% of the high-density croplands also have high population growth. 25% have high population densities, more than 75% have high fertilizer inputs, 50% high livestock density, and 20% of that land is equipped for irrigation. In Oceania, which is Australia, New Zealand, and the island chains of Micronesia, Melanesia, and Polynesia, more than 75% of the high-density cropland is arid with high fertilizer use. About 50% has high livestock density, 25% has a water stress. In the atlas, the assertion is made that there are lower population pressure and higher income. There's less population pressure and higher incomes overall in Oceania, which means the potential for degradation is reduced compared to Africa or Asia. However, land-wise, Australia dominates this area, and since the IPCC report data was collected, Australia has undergone large and long-lasting wildfires, which have killed around 500,000 animals. Some of those animals may not survive species extinction as a result. The damage from loss of ecosystem services and the possibilities of recovery of forest are not yet assessed. In South America, high-density cropland has comparatively few GCIs. More than 75% of the area has high livestock densities. More than 60% has high population increases, with half occurring in drylands. Less than 30% has high population densities, and most of these are non-drylands. Next slide, please. So this graph indicates the square kilometers of high-density cropland globally by the number of square kilometers affected by varying instances of GCIs and whether those areas are considered to be in decline. The presence of 4 to 7 of change issues predominates, even if the productivity of the area is stable or increasing. Possibly 500,000 square kilometers of land that is stable in production is also subject to more than 7 of these global change issues, which increases the risk for degradation. Next slide, please. we look at South America alone, we see that while there's some correspondence with the global observations in terms of instances of 0 to 4 and 4 to 7 GCIs in an area, high density cropland in South America showing either decline or increase in productivity and no indicators of stress or decline, still has around 70,000 square kilometers affected by 4 to 7 GCIs. Areas showing stress but maintaining productivity cover over 100,000 square kilometers, but over half of that land is affected by 4 to 7 change issues, and a few thousand square kilometers are affected by more than 7 change issues. More than 120,000 square kilometers are either showing trends toward decline of productivity or have measurable declines in productivity. This is not the worst example. Asia and Africa face greater pressure from multiple GCIs across high density cropland. Next slide. As we noted, there are many different combinations of cropland under different use scenarios. Information about land conditions in regions where these combinations appear can be found at the World Atlas of Desertification link. What does the atlas have to say about forested areas, which are important for wildlife and mitigation of global warming and are increasingly exploited by humanity? The definition of forest in the atlas is more than 40% tree cover per square kilometer. This shows over 50% of global land area, or 36.5 million square kilometers, are forested. Trees cover non-dry land areas more than dry lands. Current estimates suggest that only about 10% of forest are dryland forest. New information that became available after the AR6 publication suggests this is an underestimate, but that data has not yet been published. We can see that the biggest threats to half of the forest are population pressures, combined with the expansion of livestock into forested areas. A significant area is inhabited by low-income populations. Approximately 30%, or 11 million square kilometers, is affected by low nitrogen availability. Tree loss affects about 13 million square kilometers, while about 4.4 million square kilometers show decreasing land productivity. Next slide, please. The atlas makes some global observations on what is happening in forested areas. Approximately 43% of forest, or 15.7 million square kilometers, experiences potential pressure from 4 to 7 change issues. Land productivity decline is observed in 21% of this area. Approximately 50% of forest experiences potential pressure from 1 to 3 GCIs. Land productivity decline is observed in 10% of that area. Less than 1%, or 0.19 million square kilometers of forest experiences potential pressure from 8 to 13 GCIs. Land productivity decline is observed in 62% of that area. Around 7%, or about 2.6 million square kilometers, have no GCIs. Those regions are mostly in the northern boreal zone. Think northern Canada, far northern China, Russia, and the Amazon. So throughout the forested areas of the globe, we have a total of 5.2 million square kilometers experiencing declines in productivity. Next slide, please. The atlas makes some continental observations on what is happening in forested areas. In Africa, low per capita income, high population density, and population changes are socioeconomic GCIs that all occur in about 90% of African forest. These GCIs somewhat mirror what we observe for high density cropland. Forest loss occurs over 38% of this area, and fire over 25%. Those are the two main biophysical GCIs. Fires are very common in Central African Republic, the southern part of the Democratic Republic of Congo, Zambia, and Tanzania. Next slide, please. The extent of forest, nearly 11 million square kilometers in Asia, is the highest of all continents. Forest includes the vast boreal zone where there are very few GCIs. Tree loss affects 30% of this area. Land productivity decline affects 10% of it. Population density affects 65% of it, and low income affects 45% of it. The areas that are most affected are in the Himalayas, Laos, Vietnam, northern Thailand, Myanmar, and southern China. A GCI combination of forest loss, livestock densities, and low income occurs in the Philippines, on the islands of Luzon and Mindanao, Indonesia, and also in Papua New Guinea. Next slide, please. North American GCIs include tree loss, increasing population, increasing livestock densities, and low agricultural inputs. Forests in the southeast United States experience water stress and drought conditions. Next slide. So what does the future hold for degradation and desertification? There are many issues around land degradation and desertification that we have not been able to cover in this webinar. It includes sand and dust storms and their contributions to or deductions from land productivity, as well as their feedback effects on climate change. The effects of wildfire deserve some further elucidation, and we lack the time here to consider issues of water, especially fresh water, whose loss is arguably the major threat faced by life, as its exploitation overwhelms our capacity to preserve its sources. The continued indiscriminate human contribution of greenhouse gases to the atmosphere is the basis of all the challenges humanity faces in maintaining life on a warming planet. In a future webinar, we will examine mitigation efforts and evaluate their efficacy, as well as catalog the real solutions that are currently rejected by capitalism as being too costly to the bottom line of future corporate profits. But what the future holds, given the current situation, rests heavily on the socioeconomic factors that we have defined, which were the drivers of land, water, and air degradation. I see that Carl is asking for a break. I've only got about 7 more slides to go, Carl. If you want to, we can take a break if the rest of the group agrees to it, but hopefully I can finish here in a minute. Next slide.
We can pause for, if it's necessary, we can pause for just maybe 5 minutes. Although we should be wrapping up pretty soon. I can't see the chat, so I don't know.
Yeah, just keep going. Carl
Okay.
says just keep going. Over.
All right. Off we go. So current policies are insufficient to slow greenhouse gas emissions. Reports on emissions since 2019 show that these greenhouse gas levels continue to rise, with the burning of fossil fuel remaining as the biggest contributor in terms of tons of CO2. But what we also see are increases in methane, which is a more effective greenhouse gas than CO2. Land use change, agriculture and forestry is expanding its own carbon footprint, driven by human consumption. There's been some slowing of emissions as a result of conservation and efficiency measures, but these gains are outstripped by the increase in new emissions. Next slide. In the summary for policymakers, the 6th assessment report, special report on climate change and land, the IPCC makes the following statements. The level of risk posed by climate change depends both on the level of warming and on how population, consumption, production, technological development, and land management patterns evolve. Pathways with higher demand for food, feed, and water, more resource-intensive consumption and production, and more limited technological improvements in agriculture will result in higher risk from water scarcity in dry lands, land degradation, and food insecurity. Next slide. Policy decisions will have an effect on mitigation efforts, and while the world needs policy decisions that will cut down on the biophysical drivers of degradation, policy affecting socioeconomic conditions will also have an impact. When modeling temperature increases and predicting changes in physical conditions of land from factors such as permafrost thawing, the IPCC Also assess these changes in light of different possibilities for the socioeconomic health of the population. The socioeconomic pathways take into account a variety of possible outcomes, changes in population, types and rates of consumption, behaviors with respect to the environment, and the economic well-being of people regionally all will have an impact. Today, we're only going to look at two of those pathways. SSP1, a peak and decline in population, predicting about 7 billion people in 2100. High income and reduced inequalities, effective land use regulation, less resource intensive consumption, including food produced in low greenhouse gas emissions and with lower food waste, free trade and environmentally friendly technologies and lifestyles. Relative to other pathways, SSP1 has low challenges to mitigation and low challenges to adaptation. SSP3 includes high population growth, assumes that we have 13 billion people in 2100, that we have low income globally and continued inequalities, material intensive consumption and production, barriers to trade, and slow rates of technological change. Relative to other pathways, SSP3 has high challenges to mitigation, and it also has high challenges to adaptation. Next slide, please. To look at risk of degradation and desertification, we can look at the implications that are associated with varying degrees of increase in global mean surface temperature. Various drivers of degradation are assessed for their influence at different temperature increase scenarios. Before we look at that information, let's look at the graphical format of presentation to see how it's interpreted. The legend in the top shows that as we progress up a column, the color changes from white, impacts and risk undetectable, to purple, which can simply be interpreted as very bad. The chart in the bottom looks at this with the additional qualifier of confidence levels, which depend on agreement of lines of evidence. So, for example, if we allow global mean temperature to exceed 2 degrees C, there is medium confidence that wildfires will occur on 50% more land in the Mediterranean over and above what is already occurring. If we allow global mean temperature to exceed 4 degrees C, we will see people struggle to obtain food over much of the globe as the planet's ability to produce enough food is degraded by the impacts of global warming. Next slide. Each of these drivers is associated with increasing degradation and desertification, and shows increasing possibility of severe impact as temperatures rise. These predictions are from models. As the temperature gets further and further from the hoped for maximum of 1.5 C, the confidence in the impact declines. This is a feature of caution in modeling, but that caution should not be used as a sign that the risk can be dismissed. At these higher temperatures, there will be impacts, and depending on the region that the driver is in which the driver is occurring, the impacts can be severe. Each driver is associated with impacts on various human and natural requirements. The human impacts associated with dryland water scarcity and wildfire damage are the most extensive. Next slide. We add the shared socioeconomic pathways. If we move in the direction of increasing income equality, patterns of less consumption, and a more earth-friendly relationship to nature, we'll be better able to adapt to increasing temperatures. If we continue to overconsume, if we continue to have high rates of income inequality and we cannot adapt technologically, then every fraction of a degree of change in global mean surface temperature will bring increased risk of desertification and land degradation. Next slide. So in conclusion, whether we can reduce land degradation, which is ongoing across areas of the globe with dense populations, will depend on the commitment by the world's governments to reduce emissions and hit the Paris Accord targets by at least 2030. With the publication of the AR6 census report in March of this year, we were told by the scientific community in no uncertain terms that we have very little time to limit the rise in global mean temperature to 1.5 C. We need urgently to reduce the burning of fossil fuels to reduce atmospheric carbon dioxide. Otherwise, we will hit a GMST of 1.5 C before nations have reached the agreed upon emissions reductions, which are currently targeted for the year 2040. These warnings are despite the fact that the member nations of the Conference of Parties have exerted political pressure on the ICPCC to produce watered down findings and recommend questionable mitigation methods. Saudi Arabia, Russia, Germany, and the US are particularly culpable, as are industry actors such as the beef industry. And that's all we have for you today. Thank you very much for taking the time to attend. And we will now open the floor up to questions.
Yes, thank you very much, Wayne. Excellent work. I've got, let's see, making sure we're able to. All right, in the Q&A at the bottom, because I have not been viewing chat.
There is a question in chat. Stephanie wanted to know what roughness is referred to on the tree.
Claudia, can you go back to that climate interaction thing by chance? Any chance of that?
Yes, I just need to. Which slide was it?
It would have been
Relatively early.
slide 15. Slide 15. Slide 15.
Yeah, that's
I'm
where
on
we are.
15.
Okay. So let's see. The issue was about roughness, and they wrote roughness over the tree, so it's probably a little confusing. What they mean is that the land, and it not necessarily have to be treed, it could be rocky, interrupts the flow of air, and so when it does that, it creates varying changes in the wind that affect energy exchanges with the atmosphere. It can also change how water gets picked up in the atmosphere and distributed. I would think that surface roughness was possibly a contributor to increased precipitation. So that if you make an area smooth by cutting down all the trees, you probably negatively affect the possibility of precipitation in the area. That's just a projection based on my limited knowledge, but something like that is what surface roughness has to do with. A rocky area could be rough and have the same effects as a partially cut down forest. Okay.
Cool. Are there any other questions? I didn't see anything in the Q&A section. We'll be uploading this presentation to the, oh, Stephanie's got one. We'll be uploading this afterwards to the party's YouTube channel, so look forward to seeing it there. Otherwise, I'm just going to wait on Stephanie since she said she had one. Although I could probably give you talkie. Oh, here we go. So Stephanie asks, what stats would you point to in order to debunk one of the primary arguments for ecofascism, that being that the global South or poor nations are more responsible for climate change and pollution?
Well, I mean, that's just an absurd, assertion that I'm not sure. I mean, the first stat is that the United States, which has 5% of the world's population, consumes nearly a quarter of its energy. The second stat, I would have to refer them not necessarily to a statistic, but to history. The colonial era of development of capitalism from the 15th century onward up until the middle of the 20th century was greatly responsible for degradation of land in the global south. And there is no possible scenario that I can imagine where that translates to the global south, them being developed, them being responsible for climate change. The eco-fascist assertion that the South is predominantly responsible for climate change, I don't understand what they rested on. There's simply there's just nothing to support it. If someone can give me a number or an example, perhaps I could refute it, but well,
Stephanie, as an example, points to she says that the point to plastic pollution coming out of India, for example.
Well, plastic pollution is not an issue of primary production. Plastic is a byproduct of the oil industry. And the fact that global plastic has proliferated is directly a result of the decisions that have been made by capitalists to use plastic in the manners that it is used. If India is responsible for more global plastic, their main contribution to it is related to the number of people and their population. Now, in China, China is not part of the global south. And really, India is not either. India is always seen as one of these countries that, I don't know, they're listed as a developing nation, but they were colonized for hundreds of years by the British. And I'm sorry, not hundreds of years, many decades by the British. And like the global south, the systems of government in those areas and the socioeconomic decisions they make are all too often inherited from the models of government in the colonizing powers, and those governments make decisions that emulate the decisions of the developed world in many cases. That's dying out as new generations of leaders come on. But India, India is not going to make good decisions these days because they are now in the grip of a extremely capitalist, religious fascist movement, which is more concerned with forcing farmers and the working class into a position of permanent servitude, or actually extinction in many cases, because they want to take farming land that has been traditionally used to support the population and convert it to high intensity agriculture for the benefit of multinationals. India is not likely to make decisions clamping down on global plastic because I think too much of their capitalist class probably benefits from it. Maybe those aren't good answers, but if I can give you more examples, I'll try to come up with them.
Well, thank you very much, Wayne. And I thought that was good coverage of the question, but of course, if there are more examples we would like to examine, we certainly can. But let's see. Apart from that, I've provided a link in the chat to a viewable version of this webinar in case anybody would like to review it.
I would say that Stephanie mentioned ecofascism, I had not actually thought about ecofascism in this particular term. For there is actually, if you read John Bellamy Foster on Marx and Nature and his beginning works written 20 years ago on socialism and nature, he notes that within ecological movements themselves, there were extreme, or what he would, I guess, characterize as extreme positions taken by some ecologists that the world population needed to drop by, about 98%, and that we needed to, the problem was humans, and this was called ecofascism by some people. And what you're referring to is really just strikes me as another capitalist process to put the blame off somewhere else so they continue to make money. Over.
Yeah, thank you very much, Wayne. I'm just
Carl notes that historically the U.S. is collectively responsible for roughly 2/3 of all carbon emissions since the Industrial Revolution began.
Which is interesting because the Industrial Revolution didn't take off in the U.S., it took off in Europe. But that just kind of shows the speed with which we ramped up into industry after having killed all the natives and taken all the land over. Of course, a lot of that has to do with World War II also. The World Wars, left the America in a better position in terms of production, especially World War I. World War II was just another blow to European capitalist production, but World War I and World War II pretty effectively destroyed manufacturing capacity in Europe, with the exception of Russia, and didn't help in Russia, obviously. There's probably a long stretch of time there when the United States was the world's leading industrial producer and also consumer of fossil fuels. So I guess that didn't surprise me.
Yeah. There is Christopher left a message in questions and answers. He says, speaking on plastic, sadly, we've become really hooked on it, and phasing it out of our supply chain is going to take considerable effort. To make an easier transition for us on the planet, I am a big fan of true biodegradable alternatives, such as those made out of fungi that can we either consume or compost in theory, but there's not a lot of funding for research that I can see. Have you come across anything on this in your research?
In the future, we're going to do a webinar on mitigation and what it makes sense to do and what it doesn't make sense to do. I have read some about attempts to replace plastics, and not just plastics, but oil in general as what is called a feedstock in the general production of chemicals across the world. So those alternatives are out there. The question will be, to what extent are they funded? In the United States right now, I don't hold out much hope for it. The reason being that the United States finds itself caught in a disaster of its own making, where it has made its economy depend so heavily on the military industrial complex, and has allowed its militants, its hawks, to command such a large percentage of the public budget that there is very little in the U.S. left to spend on these things. The U.S. model is that if somebody comes up with a good idea, then they'll be able to go to the financial system and borrow money and develop it and create a business with employees and make a profit. But the truth is that to do that, there has to be some basic research done, and the basic research isn't getting done in the U.S. unless it's on military questions. Over. Stephanie's right. The next World War may be fought over water. In fact, we're going to look at that too, as when we talk about social impacts of global warming in the future.
Okay, is my audio working now?
Yes.
Okay, Carl had his hand raised in the chat. I assume he has a question. I was gonna let him talk very quickly if he'd like to.
Hey, Carl.
Hey, Wayne, thanks for a great presentation. A lot of the climate forums that I've been in talk about two additional problems that you touched on, but I wanted to re-emphasize. One is desiccation of soil moisture. So even though it may rain and the plants are temporarily hydrated, the evaporation of the soil, because it's so hot and the soil temperature is so warm, it's a fleeting hydration and doesn't last. And a lot of the soil microbes that are normally present, as well as the organics, either burn off or are not present. And so the retention ability of the soil to hold moisture is reduced with higher temperatures. And certain of our grain crops and certain of our fruiting crops will not produce food or fruit or seeds or whatever you want to call it at higher temperatures. There's a window of temperature productivity, temperatures that have optimum productivity, and we're going to be exceeding those in the lower latitudes within a few decades. And so it will not be possible to produce food with those higher temperatures. So I know it's really triggering to talk about things like sea level rise and to talk about melting of Greenland and Antarctica, which are causing severe problems, but it's going to be a food issue that's going to cause destabilization of many parts of the planet. And that's going to cause a cascading effect. And I don't think we're ready for that, because people take it for granted that when they go to the supermarket, there's everything they could possibly need. And that's not going to be the future of humanity when it comes to food production, unless, you know, we're just going to basically transform all of the kelp into food, because the land will no longer be able to produce food, like in the new climate show called Extrapolation. I think it was episode 6 or 7. People just basically eat derivatives of kelp and nothing else. So I'm hoping that the people listening really are scared of the fact that food instability is going to be the driver that's going to destabilize a lot of the world. And we really need to be aggressive on keeping it as close or below. I mean, we're already going to blow past 1.5, so I don't even bother saying 1.5. It's too optimistic. But 2%, after we go higher than 2 degrees centigrade, we're going to not be able to predict, because of all of the tipping points, how it's going to impact agriculture. And I mean, the studies even show at 3 and 4 degrees, we lose a huge portion of the planet to habitation. And I don't think the people living today are even in grasping that reality. But the trends are not good when it comes to the temperature. And I think you've seen the models. Well, the last IPCC report basically was no longer sugarcoating anything. Yeah.
Okay, so you brought up several points. To the issue of the soil not holding water, there's this concept of soils having a biocrust. that they have to have the ability for water to be absorbed and not immediately re-released. And the decline in soils that have this crust, a biological crust that prevents this water from being released is an issue. On food production, what's happening now is that the climate zones are shifting. And so what the USDA calls planting, well, I guess they call it planting zones, are shifting. And what that means is that, yes, as you say, some crops will no longer grow in some areas because the length and duration of the growing season and the temperatures that are reached in that season won't be duplicated for that crop anymore. And so what's going to happen is, at least in the short run, is these growing zones are going to shift further north, which is going to change land use patterns. And yes, it will be, as you say, people will be facing food insecurity, which we're going to cover in another webinar. In fact, that's actually a problem over much of the global south, especially in Africa now, and it threatens to be a bad problem over much of Asia. India has problems with food insecurity. Southern China has problems with food insecurity. Regarding the degrees of increase in temperature, yes, you're right. We're almost certainly going to blow past 1.5. There's just no reason to think that the world's governments are going to get up and do anything to mitigate this. And so whether we survive these increasing temperatures or not depends heavily on us reducing our consumption, on changing the types of things that we eat. We need to stop being beef heavy, oil heavy. We need to become vegan. We'll have another webinar that covers marine environments as well. So there are issues of fishing and not fishing, but people are going to have to make serious lifestyle changes to have any hope of large number of 7 billion people surviving at these increased temperatures. If we could make those changes, those social and economic changes, and we can cut down on greenhouse gases, then we will struggle with it, but there's some chance we'll survive. If we don't make those changes, then no, we won't. Hello?
Testing. Okay, there we go. Thank you, everybody, for joining us this evening, and thank you for your participation. I believe we're prepared to wrap up now. We're cresting the hour and 30 mark. So we'll edit this down, the video, and then post it to the YouTube page. I've already, earlier in the chat, I shared a link to the presentation so that you can review it if you would like. But apart from that, if there's nothing else to, oh, sorry, what?
Sorry, comrades. There was a couple more things that came up. Lizzie posted in Q&A that we must include a discussion on land use, the subject of consumptions of large quantities of meat by the U.S. and how other countries are adopting this practice.
Yes. One thing the IPCC reported on is global consumption patterns. And what has happened, especially since 1960, is that the number of calories that are produced and consumed in oil and meat has doubled. And this pattern has spread across the world, so that now we have, in addition to the American beef industry, we have the Argentinian beef industry, we have the beef industry in Chile, we have, meat producing industries in many countries that are exporting meat to other places. And this is a big capitalist money-making thing. So, and these people pressure the IPCC and the various committees of the UN to water down their mitigation methods. And one of the things that the IPCC was recently pressured on was beef production. The IPCC wants to recommend that people switch to vegetarian diets, and the beef industry is up in arms about that. Over.
Yeah, and Stephanie was asking about what John Bellamy Foster book that you're referring to.
Just a minute, I'll get it to you.
Yeah, and while he's looking for that, I just want to thank everybody for showing up, and thanks for attending the webinar, or if you're watching it on YouTube. Thanks for giving us your time. Remember, capitalism is the is the key to the destruction of us.
Foster's book is Marx's Ecology, Materialism, and Nature. This was the first book that he published back in 2000. And he now has, in the last year, a companion, a follow-on book about it. Foster, I don't know how many of you know of John Bellamy Foster. He's an academic, but he's, I guess, interested in the exotic details of philosophical underpinning of socialism. So it's kind of a dense read, but I'm working my way through it. We're going to eventually do a webinar on ecosocialism, and I expect to use much of Foster's material for it. He has this particular book was designed to make the case that that Marx did not, as many people claim, deny the primacy of nature in production. He knows that nature is the source of everything. And the argument, I guess, has been over to the extent that Marx acknowledged it. So Foster has a long and detailed treatment of the sources of Marx's ecological thinking. Over.
Awesome. Well, thanks everybody for attending. Thanks, Wayne. That was very good, very thorough. It was awesome. And if anybody's interested to joining the Eco-Socialist Working Group, if you're a member of the Socialist Party, please reach out to us. And we'd like to see more hands make less work. We've got a world to change, and we've got a world to change as quickly as we can. And that being said, I guess, Claudia, I'll throw it to you to wrap it up, comrade. Thank you for all of the work that you did as well. Wayne and Claudia did a lot of work to get this pulled together. Thanks.
Yeah, thank you, Josh. And I have nothing further to add other than thank you again, everybody, for attending, and thank you for those who participated. We look forward to seeing you at the next installment.
All right. Thank you very much.